Armstrong Flight Research Center's origins date back to 1946, when 13 National Advisory Committee for Aeronautics Engineers and Support Staff arrived in California's Mojave Desert on a quest for supersonic flight with the X-1, the first aircraft to be designated an X, or experimental vehicle, by the U.S. Air Force. The first Air Force flight to pass Mach 1 came on October 14, 1947, with the NACA following on March 4, 1948. Other X-planes followed the X-1, designed to find data related to speed, temperature, structure, control, or human physiology. By the early 2000s, NASA Armstrong was testing the first integrated hypersonic scramjet, the X-43. The air-breathing engines reached Mach 7 and Mach 10. A defining feature of many high-speed air vehicles is a loud sonic boom. Over the years, NASA tried to mitigate these booms, modifying various aircraft, like the F-5 Shape Sonic Boom demonstration, F-15 and F-18, to test theories and new technologies. Armstrong even used Schlerin imaging of aircraft in flight to better understand sonic shockwaves. And finally, 7 decades after helping to create the first sonic boom, NASA is designing a new X-plane to demonstrate quiet boom capabilities, which could make non-disruptive supersonic flight over land possible. Armstrong began flying unmanned aircraft systems, or UASs, as research vehicles as far back as the 1960s, and developed the first purpose-built ground control station for these aircraft. More recently, Armstrong and other NASA centers began working to integrate unmanned aircraft systems into our national airspace.
Southern approach.
In the 1970s, Armstrong developed digital fly-by-wire control technology that replaced hydraulic systems and eventually transferred to military and commercial aviation, cars, motorcycles, and boats. The 80s and 90s saw the center develop thrust vectoring for jets, making them more maneuverable, and investigating safety improvements for commercial aviation. In the early 90s, Armstrong began the Environmental Research Aircraft and Sensor Technology program to develop greener aircraft and study the environment. The solar-powered Helios reached an altitude of 96,863 feet during the program, and prototypes of the Predator B eventually led to one of NASA's current science platforms, Icana. A new X-plane, the all-electric X-57, promises high efficiency, quieter, more environmentally friendly flight. We are also currently testing a new morphing flap that can reduce noise and improve performance, and new control techniques for increased efficiency. While the center's initial focus was aeronautics, within 10 years it added space as a research objective. The development of reaction control systems for the legendary X-15 was critical for spaceflight. Later space work included the Lunar Landing Research Vehicle to train Apollo astronauts to land on the Moon, and lifting bodies designed to return from space and fly to a landing instead of descending under a parachute. Armstrong's lifting body track record made it the obvious site for approach and landing tests of the Space Shuttle prototype Enterprise, and later Sierra Nevada Corporation's Dream Chaser spacecraft. During the Space Shuttle years, 54 missions landed here. Armstrong was involved in testing the pad launch abort test capsule for NASA's next spacecraft, the Orion Crew Module, which will take astronauts on our journey to Mars. The capsule's instrumentation and wiring took place at the center, as did its weight and balance, center of gravity, and combined systems testing. Software for the Space Launch System, the rocket that will fly Orion into space, was tested on board Armstrong's F-18, which flew to simulate a rocket flight path. Another Armstrong F-18, this time diving nearly vertically, was used to test a radar system that helped land the Mars Curiosity rover on the surface of Mars in 2012.
How's the tow line look? Come on back, Jack. I'm having a hard time seeing it.
Always pursuing breakthroughs in atmospheric flight and operations, our center has investigated new air launch techniques that could yield dramatic cost savings for access to space and equal gains in efficiency. In addition, Armstrong's Flight Loads Laboratory performed mechanical load testing on a hypersonic inflatable aerodynamic decelerator, or HIAD, that could slow spacecraft for entry into a planet's atmosphere. In order to spur space technology development in the private sector, the center runs the Space Technology Mission Directorate's Flight Opportunities Program, funding tests in space-like environments of new technologies intended for commercial suborbital spacecraft. Among other things, the program has matured a 3D printer that can print parts and tools on the International Space Station. The center has long operated a number of aircraft for the agency's airborne science program, flying scientists around the world to study the Earth. This includes a DC-8 flying laboratory, a C-20, 2 ER-2 high-altitude aircraft, and 2 Global Hawks, all carrying instruments to study our planet and its ever-changing environment. NASA's Predator B, Icana, is used today as a science platform. Besides assisting with imaging wildfires, Icana gave us the first images of Orion returning to Earth for splashdown in the Pacific after its initial orbital flight. Armstrong also operates and maintains the Stratospheric Observatory for Infrared Astronomy, or SOFIA, a 747 with the world's largest airborne infrared telescope, yielding extraordinary astronomical data about our solar system and far beyond. As Armstrong begins a new decade, advances in science, technology, aeronautics, and space exploration are all rooted firmly in the last 70 years of its history.